The SR-71 was the fastest and highest flying operational aircraft in the world, designed for reconnaissance missions. It could fly at Mach 3.3 or roughly about 2,100 miles an hour at an altitude of over 85,000 feet. The SR-71 holds the record for the fastest and high-flying operational aircraft, cruising at Mach 3.3 and reaching altitudes of over 85,000 feet. This plane was never lost to enemy action, as its speed and altitude made it nearly impossible to intercept. Therefore, many SR-71 Blackbirds are now on display in museums. The Pratt & Whitney J58 was a powerful turbojet engine developed in the late 1950s, and it was designed for high-speed and high-altitude operations. The J58 delivered 25,000 pounds of thrust dry and 34,000 pounds with the afterburner. It was designed to operate at high altitudes and speeds, enabling the SR-71 to set these records. The J58's design included a 9-stage compressor and a 2-stage turbine. It also used a unique bleed system that diverted air from the compressor to the afterburner, providing increased thrust and cooling. So if you're new to this channel, my name is Dro and I'm an engineer at Lockheed Martin. And in this video, I'm going to show you how to simulate the SR-71's performance characteristics without having any programming experience. If you haven't already, go ahead and hit that subscribe button as well as that push notification bell so that you can see all of my content as soon as it drops. Also, leave a like or dislike as well as any comments or questions you may have regarding my content. So let's hop right into it. We will be using MATLAB and ChatGPT for this project. Now, if you don't have MATLAB, you can always download the free trial. Do not worry. I will post a link in the description. Now, we're going to be leveraging ChatGPT to gather declassified data from various sources about the J58 engine. We will be simulating the engine's performance as it approaches its top speed at just over Mach 3 and comparing that data to the actual data that was collected. Now, we're going to also be measuring the engine's efficiency by simulating its thrust-specific fuel consumption, or TSFC. Now, don't get all crazy. This number is just a fancy way of saying how much fuel the engine consumes to produce 1 unit of thrust per hour. So I'm going to be taking you step by step on how I was able to complete this. And then at the end, we will generate a % error model to compare our results to the actual data that was collected. Alright, so like I said, we're going to be using MATLAB as well as ChatGPT for this project. As you can see here, I was already communicating with ChatGPT. I was actually asking about the F-135 engine, but because it's proprietary information, we can't really touch that. So I said, you know what? I should be able to get the data from the J58 engine since the whole project has been declassified. So that's basically what I said. I said, hey, give me some information about the Pratt & Whitney J58. And it gave me a lot of information. The type of jet that it is a turbojet with bleed bypass. The max thrust at Mach 3.2, which is its top speed, which is what we're going to be simulating here in a second. Variable geometry. It talks about what makes the J58 unique, bleed air bypass, the core at high speeds to prevent turbine meltdown. So it says that we can simulate it in MATLAB. Now, it was unable to generate the data for me directly into MATLAB because I am running the free trial as well. So I just had to copy and paste it. So as you can see here, this is a MATLAB script depicting 2 different models, one for the thrust versus Mach at expected to peak near Mach 3, and another model for the TSFC versus Mach, which typically improves until afterburner / thermal limits dominate. Now you might be thinking, okay, well, that was quick. That should be the whole video. I should be able to just copy and paste this and it should just spit out the 2 models that I need. Well, not necessarily. So this is where you don't necessarily need programming experience, but you need to get into a rhythm of understanding how to communicate with AI, whether you're using ChatGPT or you're using Cursor or any type of AI. you need to be able to communicate with it, because a lot of times, especially when you're doing somewhat complicated tasks like the one that we're asking for right here, you need to be able to communicate properly to ChatGPT. And also, you need to understand somewhat what these models should be looking like. Because if they start looking kind of crazy, hey, this data isn't a good representation of what's actually happening. And so the thing is, a lot of times these AIs are going to spit information and models out to you, and they're going to tell you that it's right. But unless you know what to look for and what not to look for, you're really going to get got by these AIs. So this is where this video is going to help explain it to you better on what to look for. So let's go ahead and copy this script, post it into MATLAB, and then we're going to put it in the command window, and then we're just going to click enter. Now, as you can see, we have the top model, which is the J58 engine thrust versus Mach, and then the TSFC versus Mach number. Now, the thing is, if you know what to look for and you know what not to look for, you'll be able to look at these models and say, hey, something's not right. Something's weird. How are we going from 14.3 kilonewtons of thrust? And as our speed is increasing, because our Mach number's here, Mach meaning the speed of sound, as we're increasing higher and higher past the speed of sound, our thrust is decreasing. Why is that? Also, if you look at the thrust specific fuel consumption versus Mach number, you'll see that before it even hits Mach 1, it is increasing in TSFC, and then it does a drastic decrease, a very drastic decrease. And then it rises again by the time it breaks the sound barrier, and then it just levels out at 0. How is it that it is sitting at 0 at Mach 1.5, 2, 2.5, 3, and eventually 3.2? The lower the TSFC, the greater the efficiency of the engine. So we want it to be decreasing. So just off of a quick glance, I can determine that these models are inaccurate. But this is where we train our model to be able to give us correct information, and then we ask for the real life data, the reference data, so that we can compare the model that ChatGPT is giving us to the reference data. So I'm going to go ahead and exit out of here. So it says right here, would you like to overlay real world reference data on the plot for comparison? So I said yes. And it started to pull from NASA websites, from United States Air Force websites, Lockheed SR-71 flight manual, which has been declassified. So it started to pull from all these different sources so that it could give me actual real life reference data. So as you can see here, the green lines are where ChatGPT added new lines of code to our script. So it said, would you like to overlay real data from SR-71 flight logs or visualize the inlet compression effect? Can we do both, please? So I went ahead and added that to see what it would do. Then it said, done. Your simulation now overlays real-world reference data for both thrust and TSFC. All right, so let's go ahead and copy that. I'm going to go back to MATLAB, clear the command window, paste it, and let's run it and see what happens. Boom. So as we can see here, we still have the same simulated data. This is the real data that is collected from my sources. Now, my hypothesis was correct. As you can see, these models are not lining up with the real data at all. Not even close, to be honest. So I said, why is the simulated J58 data so different than the real world reference data? Then ChatGPT went on to say, great question. The difference between the simulated J58 performance and real world reference data comes down to a combination of simplifying assumptions and missing physical effects in your current script. Now, it wanted to change certain things like mass flow rate, mixed turbine inlet temperature, constant nozzle efficiency. Now, we're going to see that although a lot of these things are important, we're going to see that it's still not going to be enough to give us a simulated model that is going to match our reference data. All right. So now ChatGPT is telling us why it's off from the real data. First off, the inlet shock compression is not modeled. Okay. So at above Mach 1.5, which is right around here, the J58 relies heavily on inlet shock produced by movable spike on the SR-71 to compress the air before it reaches the compressor. Now, this movable spike on the SR-71 was actually something that was very notable and very new in that day and age when the Blackbird was being created. And it was a very important feature in the design of the airplane so that it can provide massive pressure rise, increased total temperature, and it was a major contributor to thrust at high speeds. All right. So it's saying, ChatGPT is saying, hey, we didn't take this into consideration, as well as mass flow is actually Mach dependent. So as Mach increases, more air enters the inlet, meaning the engine ingests more mass flow. Your script assumes a constant of 100 kilograms per second, which underestimates thrust at higher Mach numbers. Third thing that needed to be fixed was the bypass bleed, which was a ramjet transition. This was ignored. So the J58 bleeds compressed air around the turbine at high Mach to reduce turbine stress and increase ramjet style thrust. This effect is critical above Mach 2. So we need to incorporate that into our script as well. And lastly, real engine TSFC decreases with Mach, ours increases. So as you can see here, you see before we break the sound barrier, you see it increasing. We actually need it decreasing. So that's what it's saying right there. And now ChatGPT is telling us how to improve our model. Mach dependent inlet compression ratio, dynamic mass flow rate, bypass bleed flow model above Mach 2, altitude adjustment, temperature and pressure, and better fuel scheduling model based on the net thrust demand. So I said, yes, you can go ahead and implement that. So it implemented it. Now let's see what it's going to give us. All right, so as you can see, it's still not looking good. Now, I went ahead and it started offering me some suggestions, but I went ahead and took a screenshot of this, as you can see here, and I said the simulated models are still significantly inaccurate. So once again, we're training the model. We're asking ChatGPT to go deeper into the research. Why is this happening? So now ChatGPT is saying, you know what? You're absolutely right. The simulation shows the large deviations from reality, especially negative thrust and unstable negative TSFC values. Exactly what I said earlier. This should not be going this way. It should be matching the dotted line as well as, and to be honest with you, this real data is looking kind of funky as well. Why is it 0 the whole way? So we're going to let ChatGPT do all the heavy lifting, do its research, and explain to us why this is happening. So at this point, I honestly skipped a lot of this, and I basically just asked ChatGPT to implement the changes that it deemed necessary so that I could go ahead and run the script and see if it somewhat matches the real-time data that has been collected. So as you can see, ChatGPT made some edits to my code. Anytime you see the red, it means that it's eliminating that line from my script. And anytime you see in the green, it means that it's adding that line to my script. So I'm going to go ahead and copy that new script, go on Command Window, input our new script, and it is still looking really funky. So let's keep going. Once again, although ChatGPT is telling me that all fixes have been implemented, your simulation should now cap turbine inlet temperature relative to inlet conditions, ensure exit velocity is always greater than flight velocity to avoid negative thrust, which was an issue that we're having. We're having negative thrust. This blue line was going down like that, which signifies negative thrust below 0. All right, so it did fix that, but it didn't necessarily give us what we needed. And it handles TSFC gracefully when thrust is near 0. We do not need this. We don't need TSFC going up. We need it going down. All right. So as you can see, ChatGPT thinks it's did its thing, but we're going to tell it no, it didn't. So once again, I tell it, hey, thrust values as well as TSFC values are still very inaccurate compared to real data. So it begins to tell me why the simulated data is still off. No afterburner mode, fuel flow model is too naive, no inlet RAM effect. It begins to explain why a lot of these things are important. So as you can see, I told ChatGPT to let's implement number one right now, which is replace the thermodynamic model with the curve fit engine model that closely tracks real thrust and TSFC. So once we implemented that, it went ahead and updated my script. And it even asked, would you like me to provide the full updated script version in one go? I said, yes, please. We're going to go ahead and copy that and run it. All right, so now we're getting there. So as you guys can see now, this TSFC versus Mach number plot is looking way different than just a stagnant zero at the bottom. We can see that this is a more accurate representation of what our TSFC model should be looking like. Remember what I said, we want it decreasing over time because the way that the J58 was created and designed was to be more fuel efficient as it goes higher in Mach number. So as it goes higher in speed, it should be more fuel efficient. And as we can see, as the TSFC number goes down, we get a more fuel efficient J58 engine. So we're getting somewhere. Also look at the thrust versus Mach number. Now we're getting sort of a parabolic curve the way that the real data is showing us. However, we far overshot. Look, it's saying at 3.2, which is top speed, it's saying that our thrust is 264, which that is not accurate. Our thrust should be around 132 at top speed. So fast forwarding a little bit, at the end of the day, remember, our goal here is to get our simulated data to match our reference data as much as possible. So I went ahead and gave the X and Y coordinates for the reference data to ChatGPT, as you can see here. 0.5, 1, 1.52. These are all these numbers down here for Mach number. And for real thrust, I gave it 70, which you're going to see right here. Y equals 70, Y equals 85, Y equals 100, Y equals 115, Y equals 125, Y equals 130, and Y equals 132, as you can see right here. So I went ahead and plotted this whole line to ChatGPT and I said, hey, please formulate an equation that will accurately represent these coordinates because I wanted to see what it was going to spit out. Needless to say, after inputting the updated script, it spit out this graph right here. As you can see, the TSFC is starting to line up with the simulated TSFC, should I say. It's starting to line up with the reference data. However, I'm having a hard time with the thrust simulated data to be able to line up. Now, this is where I kind of went offline with ChatGPT and I just started tinkering with the equations myself. So if you look over at MATLAB, the two equations that we are concerned with are going to be our thrust values, this equation right here, as well as our TSFC values right there. So these two lines are what dictate how the simulated data curve is going to behave. So in order to get a best fit to the reference data, we have to manipulate these equations. Now, after much tinkering, I was able to get an equation of negative 2.85 times Mach values to the third plus 14.85 times Mach values to the second plus 4.85 times Mach values plus 62.85. Now, that is for my thrust versus Mach number. For my second model, for my TSFC versus Mach number, I got an equation of 0.75 plus 1.5 times e to the negative 0.7 times Mach value minus 0.5. Now remember, guys, ChatGPT already gave us those equations in the previous scripts that it was giving us. All I did was I just started messing with the numbers. I started messing with these coefficients right here. Negative 2.85. I brought this one all the way up to like 15. 62 I was messing with it from down to like 55, 49. I just kept messing with these numbers because I wanted to essentially see how it affected our plot. And like I said, after much tinkering, I was able to get a somewhat decent plot. As you can see here, at x equals 0.5, we get a y value of 70 for both plots. For the simulated data, at roughly Mach number of 1, we get about 79.5 when the reference data is calling out for 85. So you see, like, we're off, but really we're way better. We're way more on point than how we were in the previous data that ChatGPT was giving us. Once I was able to get these models aligned as best as possible, I then was able to ask ChatGPT to go ahead and compute for me a plot percent error, because I wanted to determine exactly how much was I off on all of these points. And after doing so and running this code, like I said, ChatGPT generated all of this for me in one shot. It really wasn't like these other equations that we're looking at for the thrust values and the TSFC values, where we had to tinker with them. ChatGPT knows how to compute a plot percent error on its first try. So literally all you have to do is just ask it to do it, and then to add it to your script, add it to your code, and then it'll do it. And what that yielded was this graph right here, or these models right here. Now, as you can see, I'm going to put them kind of one on top of the other. We're going to move them over here, actually. Now, as you can see, at x equals 0.5, for the thrust model, we were about 2% off. At x equals 1, so from this point to this point, we were about a little over 6% off, and so on and so forth. Then we started going down to about 6% off, 5%. Down here at 2.5, you see how these two lines cross? We go down to roughly 1.3% off. And then obviously we started going up. So we really never went above about 6.2% off for the thrust versus Mach number model. For TSFC, we're kind of in the same ballpark. We never really exceeded 6.5% off. And as you can see, it ended up decreasing drastically after that. So there you guys have it. This is how you're able to leverage ChatGPT with different applications like MATLAB. Even if you don't know the language, don't know anything about the syntax, nothing, you're still able to leverage AI to be able to get the end result, get the end product. Now, once again, if you like this content, if this type of content resonates with you, then go ahead and hit that subscribe button as well as that like button. Also, leave any comments on what you thought about this video, as well as any recommendations on future projects that we could work on. But with that being said, I will catch you guys on the next video. God bless you guys in Jesus' name.